If you've been designing large data platforms for a while, you've probably heard this question hundreds of times. What are we partitioning this table by? But in Microsoft Fabric, that should no longer be the first question. With Delta Lake liquid clustering available in Fabric Spark, we now have a more flexible option for organizing large tables and improving file skipping. But here's the important part. Liquid clustering isn't automatically the right answer for every workload. There are still situations where traditional partitioning wins. And one of them can cause some very unpleasant surprises in highly parallel merge workloads. In this video, I'll show you exactly when I would use clustering, when I would still partition, and why. Let's start with traditional partitioning. Partitioning physically separates data into directories based on the value of a chosen column. When a query filters on that partition column, the engine can skip unrelated directories and read only the partition it actually needs. That works extremely well when the partition boundary matches the way the data is queried, loaded, and managed. But the layout is fixed when data is written. High-cardinality partition keys can create huge numbers of directories and tiny files. Liquid clustering takes a different approach. Instead of physically dividing the table into partition folders, the table remains one logical collection of files. You choose clustering columns, and during optimization, rows with similar values are co-located into nearby files. The engine can then use file-level statistics to skip files that are not relevant to the query. And unlike a fixed partition layout, clustering keys can be changed later when your query patterns evolve. Before you implement liquid clustering, there is one Fabric-specific detail you absolutely need to understand. Your runtime matters. On Runtime 2.0 and later, clustering maintenance is incremental, so Optimize focuses mainly on new, small, or unhealthy files. On Runtime 1.3, Optimize can rewrite a much larger set of files, which means significantly more write amplification and capacity usage. So don't copy the same clustering maintenance strategy everywhere. First check your Fabric runtime, then decide how frequently you should run Optimize. Now let's look at the most important exception. Imagine two Fabric pipelines, running concurrent merge operations into the same sales table. If the table is partitioned by region, each writer can be constrained to its own physical partition boundary. The key is that the partition predicate must be part of the merge condition itself, not just a filter on the incoming data. With liquid clustering, those physical partition fences no longer exist. Both merge operations are working against one shared collection of files. So even when the business data is separate, the operations can still conflict. And running Optimize at the same time creates another collision risk. My first option is the simplest. Don't let the writers collide. Serialize operations that modify the same delta table. Second, use retry with exponential backoff. These concurrency conflicts are often transient, so a fresh attempt can succeed. Third, let independent producers append first. Then use one controlled downstream merge to deduplicate and consolidate the data. And finally, run Optimize as one controlled maintenance job, preferably in a quiet window away from active merge operations. Now consider an IoT telemetry table. Someone decides to partition it by device ID, which sounds reasonable at first. But with 400,000 devices, that decision can turn into hundreds of thousands of physical directories. And that is where we see true performance. Worse, the data is often skewed. Many devices produce very little data, while a small number generate huge volumes. This is where liquid clustering fits much better. Cluster by device ID and event date, without creating one physical partition per device. Here's another common architecture problem. Today, almost every query against your orders table might filter by order date. Then the workload changes, and suddenly your analytics teams are filtering heavily by customer segment instead. With traditional partitioning, changing that physical design can mean rewriting the whole table or maintaining another copy. With liquid clustering, you can change the clustering keys, then reorganize the existing data with a full optimization. Streaming and frequent incremental loads can create another problem. Every micro batch may add more small files into the current date partition. One improvement is optimized write. So incoming micro batches land as fewer, larger files instead of creating unnecessary fragmentation. Then schedule optimize to maintain the clustering. On runtime 2.0 and later, incremental maintenance makes this much more practical. Vorder still works with clustering. Clustering organizes data across files, while vorder optimizes inside each file. Keep merge and optimize separated. So what's the decision framework? For new Fabric tables, I would generally begin by considering liquid clustering first. High-cardinality filters, skewed data, changing query patterns, and frequent incremental loads all strongly favor clustering. But partitioning still has a legitimate place when independent merge writers each own a clear slice of the data. And for very small tables, don't over-engineer the design. You may need neither partitioning nor clustering. Don't ask only what should I partition by. Ask how the table is queried, written, and how that workload load will change. Then choose the physical design that matches the workload.